This is the third video in a series that I've made to explain how we can make big AI models small enough to run on your device, such as your laptop or even your phone. In the first video, I talked about quantization, which reduces the precision of a model's weight so it takes up less space and it can run faster and sometimes with very little loss in performance. And then I talked about distillation, which is about training a smaller student model to imitate a larger teacher model. Now, in this video, I want to talk about pruning, which is about removing parts of a model that don't add value. And these techniques can even be used together, which is why I'm confident that in the future, we're going to be doing lots more inferencing or using AI on our devices and much less inferencing in the giant cloud data centers. Now, imagine you've taken a family photo at a wedding. Everyone's in it, the bride, the groom, your cousins, that weird uncle, and a couple of drunk strangers in the background. The photo is fine, but 90% of what's in the frame isn't valuable. It doesn't make the photo work. The story of the photo is about the bride and groom, and everything else is the background. So you can crop it, you can cut it out, you can remove people who aren't part of the story, and the photo gets smaller. The file size drops, and somehow it even looks better. That, in simple terms, is model pruning. When you train a neural network, you end up with millions, billions, or sometimes hundreds of billions of weights. A weight is just a vector that sits inside the model to influence how information flows through it and how strongly one part of the network affects another part of the network. Some of those weights are doing the heavy lifting, but others contribute very little. Weights with high values are much more likely to make a difference. Pruning essentially is the process of identifying the parts of the network that don't contribute much and removing or disabling them. You're trying to keep as much of the model's intelligence as possible and just throw away some of the excess. And if you do it carefully, the model becomes smaller, it uses less memory, and in some cases, it even runs faster too. And the performance drop can be surprisingly small. So how does it work? Well, let's go back to the wedding photo analogy. The file might be 12 megabytes in size with a few thousand pixels in either dimension. With so much data to play with, you can choose what happens. You want to keep the bride, the groom, and the parents on either side, maybe 6 people in total. Now, you could, for example, put the photo through something like Photoshop and just erase out the details that aren't contributing much, like Photoshopping somebody out. The dimensions of the photo don't change, but a lot of those pixels now are blank or they've been smudged into the background so you don't even notice. And this is similar to what you'd call unstructured pruning in neural networks. You remove the individual weights in the model, but the structure of the model stays the same. And so this can reduce the amount of useful data that needs to be stored, but your hardware must still process the same overall shape of the model. It's now just got a lot of zeros sitting inside it instead. So you might save some space, but you don't always get a meaningful speed boost. Now, there's a second technique called structured pruning, which is instead of erasing tiny details one by one, you crop out one side of the photo because nobody important is standing there, and you cut the top off because it's just the ceiling. The photo is genuinely smaller in every dimension. And that's closer to what we call structured pruning. So instead of removing the individual weights, you remove the larger units of the model, maybe whole channels or neurons. It's less flexible than removing weights one by one, but the payoff is much better. And that's because the network itself becomes much smaller in shape, and that's far more likely to translate into faster inferencing on hardware. So unstructured pruning might be more precise, but structured pruning is more useful in the real world. And now there's an even more advanced technique called magnitude pruning. So imagine you've got a model with millions of parameters, and this time you prune off a smaller chunk, maybe 10%, and then you fine-tune the remaining model. The surviving weights adjust to compensate for some of what was lost. And this is called iterative magnitude pruning with fine-tuning, which is a hell of a mouthful. But what you do then is you pick another chunk, you retrain and fine-tune again. You prune, retrain. And this whole pruning process is really a lot like growing roses. And that's because every year to grow roses well, you need to cut them back, not because you hate your roses, but because the extra growth is not always helping. So you help the plant by removing what's unnecessary so the plant can direct its energy where it matters the most. And this technique is very similar to that. So simply making a model bigger does not automatically mean that it's designed better. Sometimes it just means there's more garbage inside it. So in the last 3 videos, I've covered quantization, distillation, and now pruning. These are 3 different ways to make the model smaller without losing too much information. And that's really important because the future of AI does not have to mean that every task gets shipped off into an enormous cloud data center. And if we can make our models smaller, leaner, and more efficient, then more of those models can run on local hardware on devices you already own. And that means faster, cheaper, and more private. Now, to be clear, we still need to train these big models in the data centers, and many of these techniques, such as quantization, distillation, and pruning, may also need to be done there as well. But the result is smaller models that can be cut down to size. And this is the direction where the technology is heading. I'm Dr. Errol Brandt, the founder of Kiraa. Please feel free to share your thoughts in the comments. Thanks again for watching, and until next time.